Okay, and then I'm going to share my screen. All right, so this, let's see here. I think we were somewhere near here. Uh-oh. Sorry. Throwing my is this working? Yes. Okay. Let me move some notes so I can actually write on my Wacom. Sorry. All right. So I think we were maybe here talking about osmotic pressure, and this was the form of the equation showing that osmotic pressure is a way of getting molecular weight. And for real solutions, there's a non-ideality expressed as a virial coefficient times these parameters, RTC2. Okay, and let's move this back down here so it's not in your way. All right. And probably the last thing we talked about was the fact that this is an inverse molecular weight. So the native aldolase has a smaller intercept. I have a larger molecular weight. You can see over here, it's 160,000. The subunits, it's a tetramer. We have a higher intercept, a smaller molecular weight, but notice its slope is bigger because this is under denaturing conditions. So they're extended chains. They're approximately random coils. So the compact structures have smaller virial coefficients, less excluded volume, even though it's a tetramer, than the subunits. Okay. What they cover in the book, and I don't think I think I stopped before this, or if not, I'm repeating that last part of the lecture. If it's a mixture of macromolecules, then the osmotic pressure is the sum of osmotic pressure over all solutes. And each individual one will obey the simple osmotic pressure equation, where it's the concentration of that component divided by the molecular weight of that component. So consequently, the total osmotic pressure will be the sum over all of these terms. The RT is taken out because it's constants. So it's the sum over C sub I, M sub I. And then what he does here, what anybody who covers this does, is they multiply and divide by the total concentration, where the total concentration is equal to C, but you can also write it as the sum over C sub i's. And so they sum to the total concentration. Okay, and so in doing this, what they do is they take this sum over C sub I, M sub I, and put it into the denominator, but they put it on underneath a quotient. So when you multiply this out, it would come back out on top. But then they multiply and divide by total concentration. In the numerator, it's expressed as C. In the denominator, it's expressed as sum over C sub I. So you get this term here, sum over C sub I divided by sum over C sub I divided by M sub I. All right. This is the definition of a number average molecular weight. And it essentially is the definition of what we use for colligative properties, properties that count numbers of particles. Okay, and so this expression can be rewritten as the osmotic pressure is equal to RTC, total concentration, divided by number average molecular weight, because that's what this is. All right. And then in the real expression where you have a virial coefficient, I couldn't find a B with a bar on it, so I drew it in. You have an average virial coefficient that reflects the average from multiple species, and we're not discussing how one calculates that average. We'll just call it an average virial coefficient. So it becomes an RTC over M sub n. That should be subscripted. It's a funny font as well, plus this virial coefficient term. There's a table in the book describing different kinds of averages. It's described in terms of numbers of particles, or it's described in terms of concentration. There's something called a number average, a weight average, and a Z average. There's actually a Z+1 average and N-1 average. There's a whole series of these that one can mathematically express. Notice it follows a trend. It's M sub I in the numerator, it's M sub I squared with an M in the denominator, it's M sub I cubed in the numerator with a M sub I squared in the denominator. So you add in multiples of M in both the numerator and the denominator to convert between these different values. I say up above here, a number average is a number concentration, and it's a colligative property: osmotic pressure, freezing point, boiling point, elevation. So different averages will not be the same unless the sample is homogeneous. So if it's really a single species, you'll get the same molecular weight. If it's a heterogeneous mixture, then the number average will be less and the weight will be less than the Z. It's because it goes as the square of the molecular weight, or the molecular weight or no molecular weight in the numerator. It changes the relative contribution by adding this square term in terms of concentrations, for example. Different methods give you different values. Okay, so osmotic pressure generally gives you a number average molecular weight. Methods that I use can actually be formulated in a way that can give you mixtures. I can get the number, the weight, and the Z out of the same data by the way I manipulate the data. Okay. So the next thing we're going to look at is simple dialysis experiments. And Van Holde likes to do this little discussion of a simple dialysis experiment where you have a protein inside a bag. That is, the bag will not allow the protein to go through, so it has some kind of a cutoff molecular weight. We generally do this with bags that might have a 10,000 molecular weight cutoff. You can find bags that have different kinds of cutoffs. There are filtration methods that do similar sorts of things. And then you put a ligand into the buffer that the bag is sitting in, and then the ligand can penetrate. Okay. So the molecule, the macromolecule, is trapped. The ligand is then in the solution, and it can equilibrate across the bag. Okay. And so the solute will eventually come to equilibrium across the bag, and it will have equal chemical potentials in the bag or in the solution is the idea. Okay. So the alpha phase is inside the bag, the beta phase is outside the bag. All right. And then he makes these simple sort of analysis to ask, how does this work? And ignoring small pressure differences, you basically get a concentration times an activity coefficient in the bag and outside the bag. And so this implies that it's a concentration times an activity coefficient in the bag, concentration times an activity coefficient outside the bag. And that implies that you will have equal concentrations of solute inside and out. The problem is that there's a difference between bound solute or bound ligand and unbound ligand. So the bag will actually accumulate extra total ligand if it binds. Okay, and so this implies that there's some distinction between what's bound and what's unbound, and you have to sort of do a calculation to determine differences between bound and unbound and how you might calculate that. This isn't necessarily easy to do at low affinity. And so sometimes the number that comes out implies negative binding, that there's actually less material in the bag than outside the bag, and it seems as though there's some exclusion, right? This can happen simply because the macromolecule excludes volume. It doesn't actually bind to the ligand, but the ligand sees less volume, and so there appears to be less of it. Okay, and a lot of this depends on how you make the measurements and how you do the actual concentration determination. So he's implying in this that simple calculations inside and outside the bag don't necessarily work with low affinity situations. That discussion was for a non-electrolyte molecule. In other words, a macromolecule that has no charge. If a macromolecule or a biopolymer is a polyelectrolyte, meaning it has multiple dissociable groups of some kind, then necessarily by charge-charge interactions or by net charge in the solution, there has to be some electrolyte that's associated with the protein. So if the protein has an average net charge of plus Z, I was just reading something about average charge, then there must be Z ions associated with the protein. And you can't have basically a protein isolated from its neutralizing electrolyte. So this is written as plus Z. It could implying a positive charge. This could also be written as minus Z, so that the counter ion is actually a cation, not an anion. So this would work regardless of how you do this. So if X is monovalent and P plus Z is polycation, okay, and all you had was the protein, okay, then you would necessarily have to have the counter ions. All right, and the counter ions would have to stay in the bag. So this is essentially saying in the absence of excess salt. All right, and so they must stay in the bag. But what that means is you have one protein and Z anions. And that means you have Z plus 1 particles in the solution. The number average molecular weight counts particles or particle differences across a reference and the beta side and the alpha side. So when you measure a colligative molecular weight, there will actually be a correction term for the number of particles. And the molecular weight will come out to be the average between the molecular weight of the protein and the molecular weight of the anions. So it will give you a funny low value in the absence of salt. All right, so this, it turns out, is one of the reasons that we perform experiments in low molecular weight electrolytes. We usually do experiments in 100, 150 millimolar salt. I'm saying sodium chloride here, but it could be any number of things. Biological solutions also have appreciable amounts of salt. Okay, generally speaking, it's around 150, 170 millimolar in solutions like serum. Okay, so if you have a protein with a charge and an excess of salt, Then to study this, you basically have to take into account the fact that the salt itself dissociates into its cation and its anion. The chemical potential across the bag, inside to outside of the salt, is assumed to be equal. And notice we're not writing down a chemical potential for the anion or the cation. They necessarily go together. They can't go independent of one another. You can't have a solution of just sodium. There has to be a counterion. Same reason. So you can write this down in terms of a chemical potential being equal to its standard state chemical potential times RTLN, and notice it's concentration of B times concentration of X. Okay, so you end up writing down some average the product of some average concentrations, which initially we assume is equal. Okay, and so these are the molar concentrations of B and X. Okay, so if we neglect the difference between the standard state on both the alpha and the beta side for approximations and to make progress here, then what this implies is that the concentration product on the alpha side, CB times CX, is equal to the concentration product on the beta side, inside the bag, outside the bag. Okay, so it's CB times CX in the beta phase, CB times CX in the alpha phase. This is equation 271. I'll come back to that. Okay, so I've kind of copied some things out of the text, and then I've made some comments to take us through. So the other thing that you need to take into account is charge neutrality. All right, and so here we're just looking at concentration of salt. But inside the bag, we have a charge on the protein. So the concentration of the protein times its charge is the total amount of plus charge we have, adding the concentration of the cation on the inside the bag. And that must be equal to the concentration of anion inside the bag. So the anion concentration has to match the sum of the salt and the protein, okay? This reflects the fact that there's a fraction of the anion that neutralizes the protein charge, as reflected in this equation at the top of this slide, all right? On the beta side, outside the bag, you just have sodium chloride. You just have cation and anion, and they must be in equal concentrations. All right. So if equation 271 is correct, the product of the concentration of B times X inside and outside the bag, and charge neutrality is correct, then we can rewrite this equation. This is the 271 written over here to the left. Is that correct? Alpha, beta, BX, alpha, beta, BX. And I turned it around because the book turns it around. In the book, nope, sorry. In the book, the alphas are on the left, the betas are on the right, but then here they have the product of the betas here. Okay, and so because CB is equal to CX, and that equation was written as CBCX, I can substitute for CX and put in a CB. And so I end up on the left with CB and the beta phase squared. They're equal to one another, so I can make a substitution. On the right side, I can have a CB alpha, but then I can substitute in a value for CX alpha that is equal to the plus sum, ZCP plus CB alpha. And if you multiply that through right there, let's see if I can make this work. Does this give me a, there we go. This was CB alpha times CB alpha plus ZCP. Okay, that's what's here. I'm substituting for CX, this CX, and I'm putting this in, but then I'm taking the CB alpha out. So that's where I get the CB alpha squared. And to correct for that, I have to put a denominator in here of CB alpha. Okay, so I get this C squared term and this 1 plus term. All right. I can then do the same thing, but now I'm going to substitute CX beta and put in a CX beta for CB beta. So I have this product, CX beta squared. And then on the right, I'm going to have CX alpha, and then I'm going to substitute for CB alpha. But the substitute to solve for CB alpha, I have to bring the Z on the other side. And so I'm going to get a CX alpha minus Z times CP. So this will be CX alpha times CX alpha minus, where'd it go? Oops, there we go. Minus ZCP. And then when I take this CX alpha outside, I'll get a squared term, and I have to divide by CX alpha inside. All right, so what this says is that the alpha side, okay, has an excess of some terms, and then it has a diminishing of another term, okay? And so we have to have a little extra of one ion to account for the neutralizing the protein, and therefore a little less of the other ion, so that the products are still equal to one another, but there's a slight excess of one and a slight diminution of another. And that's expressed in this plus term and this minus term, okay? And so this is simply plugging numbers in using charge neutrality and the previous equation that involves the product of C sodium times C chloride, or whatever the counter ions are. So then I take the square root to both sides. And when I take the square root, this becomes CB beta is CB alpha times this term square root raised to the 1/2 power, and CX alpha, CX beta is equal to CX alpha, and then the square root of this sum term. Okay, so that's easy to see, I think. All right. All right, and so what this implies is what I just said, but this is what the text says. B is more concentrated in the beta phase than in the alpha phase, where the anion is more concentrated in the alpha phase, since it is the counter ion. These concentration differences will contribute to the osmotic pressure, okay? They'll be small depending on the protein charge, but they'll be measurable and contribute to the osmotic pressure. So we've assumed ideal behavior at the moment, so we're not even talking about virial coefficients. The total osmotic pressure, therefore, can be written as RT times the concentration of the protein plus the concentration difference of the CB term, plus the concentration difference of the CX term, okay? And so these concentration differences will contribute to the osmotic pressure. All right, so go back and notice that this is times 1, okay, here, and we can actually do differences. Let me go down here again and be sure. No, I'm sorry, that was a misspoke again. This is CB beta is equal to CB alpha times a square root term. Okay, and so what we're going to do is we're going to expand the squared term with what they call a binomial theorem. Okay, it's basically a binomial expansion or a Taylor expansion. Again, if you go to that math site that I sent you a link to, there's a discussion of what Taylor expansions are, or binomial expansions, and how they're sort of derived for each situation. It's basically a polynomial that approximates the shape of the curve. So when you do this, you will get an expansion in both terms. Because one of them is a 1 plus, you will have a term that's Z CP 2 C beta alpha. Notice back here, it's Z C plus C beta alpha. That's what gets expanded. All right, but then there's a 2 in the denominator. And then the next term is a negative sign. And there's an 8 in the denominator. And you'll notice that all the terms are squared here. So it's first power, square power. And it's the coefficient that ends up being different as you work your way through this. But then the second term, it was a minus ZCP over CX alpha. And so the binomial expansion gives you a minus minus. You'll still get this 2 in the denominator and 8 in the denominator, but there'll be a first power of CP over CX and a square for the ZCP over CX, okay? And now what you do is you essentially sum these terms to get these differences here. Notice the difference is CB alpha minus CB beta. And so we're going to take differences. So we're going to rearrange and combine terms and find that the CP term cancels. It cancels, it cancels because when you combine these terms, this is a plus and this is a minus. So these two terms cancel one another. And you'll get this CB alpha minus CB beta plus CX alpha minus CX beta. So when you do this rearrangement in algebra, what you'll be left with is this Z squared CP squared over 8. So in other words, sorry, wrong way. In other words, these two terms will sum, but then we're going to take the CB alpha and the CX alpha outside. Notice when you multiply this through and rearrange, this CB alpha squared is only CB alpha to the first power, and CX alpha squared is actually CX alpha to the first power. So that will cancel when you combine all these terms. And so you'll have these two differences, and you'll have this Z squared CP squared times divided by 8. And then you break it up into two terms where you can combine 1 over CB alpha, 1 over CX alpha. Okay. Higher order terms will be neglected, essentially. He says nearly canceled or smaller. Okay. So the result will be this type of an expression. Now, he then makes an approximation that this 1 over CB alpha, 1 over CX alpha, remember alpha's in the bag. These are slightly different concentrations, but they're approximately the same. One is slightly bigger, one is slightly smaller. So the sum is approximately twice the concentration of the total salt. The salt, for example, that's in the outside of the jar, outside of the bag. Okay, so this approximation allows you to put 2 over CBX in the equation. When you do that, the 2 cancels the 8 and you get a 4. And the CBX will be in the denominator because this term will multiply through. Okay, so this is basically the total concentration in the bag. All right, now the total concentration in the bag involves the C protein. It canceled in this salt effect, but it doesn't cancel for the total protein concentration. That was here. This doesn't cancel, but it's these terms that were expanded, and the CP term canceled out there, but this term is still here. Okay, the CP alpha. So you'll have a CP alpha term, a CP term, and then you'll have this Z squared CP squared 4 CBX. So when you plug this in, okay, you'll have an ideal expression. And then you'll have this other expression that arises from the small difference in counterion concentrations. It involves C squared 4 CBX, and he changes units here. I don't think I pointed that out at the beginning, but if we write this in terms of grams instead of moles, maybe up above we did say the term that we're putting this in molar. But if you then convert molar to grams per liter, to do that, you have to divide by the molecular weight of the protein. So when you do that, you get a CP in the denominator. This CP squared becomes grams per liter in the numerator and a mole molecular weight of the protein squared in the denominator. So this term essentially shows up because the counterion is readjusting due to the protein charge. Okay, he calls this a pseudo-non-ideality. This is what is known as the Donnan effect, and it varies as the charge over the mass squared. There's a Z over M squared, but it's reduced by the salt concentration. So let's go back and look at that. Z over M squared times the concentration of protein squared, but divided by the salt concentration. And remember, the salt concentration is 150 millimolar if we raise the salt concentration. So depending on the charge, this can be a large effect because it goes to Z squared. But depending on the salt, we can diminish this. Okay, so the amount of non-ideality due to this pseudo-non-ideality. This is not a traditional virial coefficient in the way we would derive B, but it is in fact a B because it's the charge effect. It will go away if Z is 0. It will go away or be reduced by raising the salt concentration. Again, this is why we do experiments in higher salt concentrations. I'm telling you 100, 150, but depending on the charge, that may not be large enough, okay? All right, so the Donnan effect is basically a virial expression or a virial coefficient caused by charge. It goes as Z squared, it's Z over M squared, and it goes as 1 over the salt concentration. All right. This is described as an osmotic pressure effect, where you've separated the protein from the solvent inside a bag. All right, so the figures in your book show a box with a bag in the middle, and the bag has the protein, it has counterion, and then the outside has counterion. And the charge on the protein is what causes this to happen. However, anytime you separate protein from a buffer, then you will have a reequilibration across that concentration divide. So for example, if you do size exclusion chromatography of some kind, where you pass a protein over a column, you put it on basically as a slug of protein or as a thin layer of protein, where it's now equilibrating with the buffer in the front edge and in the trailing edge. And so it's necessarily got a distribution of charge species. When you do any kind of diffusion experiment, that is in fact some kind of a diffusion experiment, you don't have to have a divider. Anytime you have a protein diffusing, the counterion has to go with it. And what goes with it is influenced by this pseudo-non-ideality. We will talk about this a little bit in sedimentation as well, where you have a boundary that sediments, and anytime you create a boundary, anytime you have a charge, a separation of the polyelectrolyte from buffer, any kind of concentration gradient, you will have a Donnan effect. You will have a charge effect. The other thing is that this was just derived with sodium chloride. It was just derived with a 1-to-1 charge. But if you have counterions that are 2-to-2 or 1-to-2 or 2-to-1 or mixtures of different counterions, then that original equation up here will be different. And the amount of anion that's associated with the protein will depend upon the charge. Okay, so it will not be Z if this was a -2. It will be Z over 2. And necessarily, depending on what B is, there will be some equilibration that you have to take into account as well in the electroneutrality equations. So the electroneutrality equation will also have to take that into account, okay? Because it's a charge effect that you're looking at. All right, and so you will get different results depending on the counter ion that's in the solution. So the point of all of this is that when we have real solutions, non-ideal solutions, the total virial coefficient will include an excluded volume term and a Donnan effect. And the Donnan effect will be the bigger effect at lower salt. However, if you add salt, it will diminish the Donnan term and the excluded volume term will become predominant. And so the total calculation of the excluded volume and Donnan effect is a sum. It's the sum of the excluded volume term. I think for spheres up above, the equation was something like 4V bar over M. For rods, it's something like L over D, V bar over M. Okay, so those are the excluded volume terms, depending on what it is. The Donnan term depends upon Z and salt concentration. So in the book chapter, the question that's going to be in the assignment, I think it's question number 7. I'll go to it in a second. It's a problem that involves double-stranded DNA. Okay, so it's effectively a rod. The equation requires V bar, the partial specific volume of DNA. The DNA field usually uses 0.55 for typical salts, sodium or potassium chloride. Okay. The charge depends upon the number of bases. So in a double-stranded DNA, depending on the length of the oligonucleotide, the charge will be -2 times the number of base pairs. All right, so that's where the total charge will come from. And then the question doesn't give it to you, but typical salt will be 100 to 150 millimolar. So you should use V bar 0.55. You should use salt of something like 100 millimolar. Okay. All right, so let me keep what I have written and here. Oh, that's the wrong, what are you doing? Okay, my software is deciding to reboot for some reason. Okay, and I think I don't have the document open. I gotta go back and open the document. And I think it's is it this one? No, it's not that one, sorry. This one. No, it's not that one either. Goodness. It's this one. Sorry. You have these two. So it's this right here. Okay. Double-stranded DNA, molecular weight, 100 base pairs. Behaves like a rigid rod. It gives you dimensions, length and diameter. They want you to estimate B for a 1 mg per mil solution, assuming every phosphate residue is charged. Okay, and they want you to assume an excluded volume term and the Donnan term to get a total B. Okay, repeat the calculation with a more realistic assumption that 80% of the charge will be neutralized by condensed counterion. And so this is an important feature. When you have charge, so this will be double-stranded DNA. That's terrible double-stranded DNA. Goodness, I'm making it worse. And you have negative charges along the DNA. All the sodium ions are associated with the DNA. They actually bind to the minor and major groove of the DNA to neutralize the charge. So what you see out here when you're looking at the DNA, what you can actually see in the solution is not the charge that you could calculate for the DNA. It's the charge through this condensed phase of sodium ions. And so that's where the neutralization of charge comes from. So in this first part, the charge is going to be something like minus 200. And then in the second part, the charge is going to be something like 40, 80% neutralization. Okay, so you're going to calculate it twice. All right. Let's bury that. Let's close that. Okay. This last little topic discusses, we're not going to spend any time on this for the sake of time. This last discussion discusses that Donnan effects also apply to equilibria across membranes and passive, facilitated, and active diffusion. And the chemical potential there will also depend on electrochemical potentials across the membrane. You discussed this somewhat with Dr. Hostler in medical biochemistry. I'm not going to go through this just for the sake of time. Okay. And this version of the PowerPoint I'll now post out there so that it has everything caught up in terms of what the document should be. I'm going to save that and then I'll copy it later. So it's out on the website. Okay. So what we want to do now is move on to chapter 15. And chapter 15 okay, so this is what I just did. I'm going to save this as well. Save so that anything I wrote out here will also be saved in the document. And then I'm going to close that. And then I think that means I don't have this document open, probably. I don't. So I have to go back over here and open up chapter 15 here. There's also a version of this in the book version, which I may have to open up later, depending on what I'm doing. Okay, so we're going to now go to this next PowerPoint. And this has to do with chemical equilibria involving macromolecules. Okay. So this is a slide from the previous lecture where I messed stuff up a little bit and I tried to rewrite this equation down below. Okay. And so the expression was written in a way that we multiplied through all of these terms to be able to derive at equilibrium, multiply and divide by this expression. I was talking about this, but basically we're making a substitution, this substitution up above in here, and then all of these are equal to one another because of this expression. And so you can take them outside. It's equal to 0, so these terms will cancel. So this is the general equilibrium expression. When you have a multiple equilibria problem, A moles of A plus B moles of B going to G moles of G plus H moles of H. The equilibrium expression is A times chemical potential of A plus B times chemical potential of B is equal to G times chemical potential of G plus H times chemical potential of H. Remember, there was a sign, I think there's a sign error here. All right, so this chapter begins with this expression. They write down this very expression, AAs and BBs going to P. In this case, they've changed it to P and Q, all right? And then they write down a general expression. This is written in the previous chapter as G final minus G initial. Delta G Gibbs free energy is a state function. And then we end up using the same expression, okay, that delta G involves P moles of P stoichiometry in the reaction times the chemical potential of P plus Q times chemical potential of Q. Notice here the signs are correct so that when you set this equal to 0, you can set them on opposite sides, okay? But at this point, we're not setting this equal to 0. We're simply going to solve for this expression. Each one of these can therefore take this general expression for the chemical potential of species I is equal to the standard state chemical potential plus RT-ln, the concentration of species I times the activity coefficient of species I. In this case, it's written as a Y. Okay, these are in molar concentrations, and throughout most of the part of the book, this was an F or it was a Y or it was some kind of a gamma function, depending on the concentration units. Okay. So this is the general expression for the chemical potential. And so you can take this expression and plug it into equation 14.2. I've stolen this out of the book chapter, but this is similar, if not identical, in chapter 15. Okay. And so when you do that, you end up with these two terms for every one of these terms. So every species will have a standard state, and it will be a standard state times P, the stoichiometry, plus the standard state of Q times small q, and then minus the standard states A times chemical potential of A, standard state, B times standard state of B, etc. So there'll be a series of terms that are standard state terms, and then there'll be a sum of RT-ln IY. All right. And so these can be combined because they're logarithms. All right. And the product of a log, the log of a product is the sum of the logs. And you'll get quotient involving numerators from the positive terms and denominators from the negative terms. And so the log of a quotient is the difference in the logs. Okay, so all these plus terms in terms of the log term will end up in the numerator, and all these negative terms will end up in the denominator. And then in addition to that, when you write down this equilibrium constant for this term down here, it's P raised to the P, and it's Q raised to the Q divided by A raised to the A and B raised to the B. Okay, and so that ends up being taken into account because of these products by P, Q, A, and B. And so PYP will be raised to the P power, and QYQ will be raised to the Q power, and AYA raised to the A, and BYB raised to the B. So this is essentially the equivalent of what will become an equilibrium, equilibrium constant, as long as the concentrations are at equilibrium. But if they're not at equilibrium, then it will be whatever these concentrations are at that point. So if you combine all of the standard state terms, this will be the overall standard state for the equation. And then there'll be a term that involves the concentrations raised to the appropriate stoichiometry. So this will be the concentration term. And then this term will be able to be split up, and these will be the activity coefficients. So again, these terms can be broken up into two natural logarithm terms, simply because it's the logarithm of a product is the sum of the logs. Okay, so there'll be a standard state term, there'll be a concentration term, there'll be an activity coefficient term. So in the medical biochemistry lecture, I simply generated this equation by writing it on a slide. And I said that in a different course, I will derive this, where I derive these terms from sums over the chemical potential equation. Okay, so if you went back and looked at your medical biochemistry lecture for thermodynamics, this line is in that lecture, and here's where we just did it. We just plugged these into the chemical potential expression. Okay, and so it will involve products, the sum of the products, divide by the product of all of the reactant concentrations. Okay, and then we went through a series of using these equations to solve problems. And so when you go back to that, you'll see how we use these calculations. In all of these calculations, it's concentrations. It's not, there's no activity coefficients. And what we're doing now, we're allowing for the possibility of non-ideality. Okay. And so I put those slides in simply to remind you where this all came from. So that series of equations then will lead to that expression. The free energy is equal to a standard state free energy. This is the sum of all those standard state terms, plus the RTL and the concentrations of all of the different terms multiplied out. And it's P raised to the P power, Q raised to the Q power, etc. Now in the book, Van Holde does an example. And the example he does is hydrolysis of ATP to ADP plus phosphate. And he gives an approximate value. And then he describes the fact that as you change concentrations, the value will get more negative, more favorable. Okay, and so this is described, and this is the way he writes out the equation: ATP plus water going to ADP plus PI plus a proton. So the phosphate is lost, a proton is lost. The water and the phosphate and the proton get incorporated into other terms. Remember in our discussion then, the pH is usually fixed by a buffer, and the water is a high concentration, 55 molar approximately, under dilute conditions. And so they end up getting incorporated into the standard state. And we wrote that as a dagger to account for the fact that it was pH 7 or something, all right? And so the expression involves the product of the ADP concentration times the phosphate concentration divided by the ATP concentration. Okay, and there's no stoichiometry term, so this is the expression. Okay, again, in that lecture, there's an example of a typical question that I ask in exams, where I give you the standard state free energy. Here it's in kcals, not joules. I give you an initial concentration of ATP and ADP and PI. I give you some approximations for the RT 2.303 term. And then I ask you to plug numbers into this equation and solve for the standard state, for the total free energy change under these conditions. So remember how this works. Under any given set of conditions, that will give you the free energy. They are not equilibrium conditions. This gives you the equilibrium standard state free energy. And then you correct that for the whatever the concentrations are. The ADP is 0.5 millimolar. The phosphate is 10 millimolar divided by the ATP, which is 5 millimolar. And then this will give you some number here on the left, okay? The difference between that course and this course is I wouldn't give you this kind of a multiple guess. I would actually make you plug numbers in. Okay, Chapter 15 gives examples of pHs, conditions, and standard state free energies for various kinds of reactions. A lot of these are hydrolysis reactions where you're cleaving phosphates. I gave you a similar table in the lecture last time, showing you what the various values are. It also gives you some standard state values, not just for the free energy of total hydrolysis, breaking down these molecules into their particular atoms, but it also gives the enthalpy of the reaction, okay, for total hydrolysis, what the total free energy is, what the total heat is, okay. The book goes through some similar calculations at equilibrium. Delta G would be equal to 0. It would be the standard state. We can rearrange this equation, and this would give you delta G naught is now equal to minus RT-ln, where all of these concentrations are equilibrium concentrations, and therefore this becomes an equilibrium constant. Okay, so again, the standard state is the equilibrium expression, and then the given concentrations, how much it deviates from equilibrium, that actually determines what the free energy or the driving force for the reaction is. Okay, and so here's an expression for the free energy, and down below it expresses what I just said, that the first term is the equilibrium expression, and the second term is the actual concentration under those conditions. Okay, and the book puts in the subscript equilibrium. Okay, so I think I went through this in the previous expression, in the previous lecture, the Med Biochem lecture, and here in the book, he's doing the same thing. Once you get those equilibrium expressions, and this is from the previous lecture, I've just grabbed a slide, you can plot ln K versus 1 over temperature, and the slope of that line will give you the enthalpy. It's the ratio of RT, delta H over R, because you're plotting it versus the 1 over T. And so this is the slope. M is the universal expression for a slope. Okay, and so this is what we described before in the calorimetry expression for a Van Hoft free energy change. Okay, and so for similar kinds of expressions, this is the connection to what we had done previously. Okay. Now, at this point in the book, there's a section in either the book or the book chapter that I gave you. There's a series of measurements for different kinds of experimental expressions. This is labeled, the header is labeled interactions between macromolecules. And it gives the free energy for the reaction. It gives the enthalpy, it gives the entropy. It also gives something that we'll talk about, which is the free energy per monomer. And what it does is it lists a series of reactions. So this amino acid oxidase is a monomer dimer equilibrium. Here's the free energy. Notice it has a 0 enthalpy and a plus 1 over 4 entropy. So this would end up being an entropically driven reaction. Arginosuccinase is a monomer dimer equilibrium. Here's its free energy. Notice it has an unfavorable enthalpy and a positive entropy. So this is also an entropically driven reaction. The enolase is also monomer dimer. Necessarily, the free energy, the equilibrium is negative, otherwise the reaction wouldn't occur. The enthalpy is negative, so it's enthalpically driven, but the entropy is also positive, so it's also entropically driven. And then there's a series of other reactions. So this is a indefinite polymerization, P plus Pi going to Pi plus 1. It will grow indefinitely. Notice there's a 0 enthalpy, entropically driven. Hemithrin, monomer octamer, no enthalpy, entropically driven. Insulin undergoes a series of reactions leading up to a hexamer. Okay, The first two reactions are entropically driven. Notice there's an unfavorable entropic expression, but then the final equilibrium to the hexamer is unfavorable enthalpically, but favorable entropically. And then beta-lactoglobulin, 4 dimers to make an octamer, enthalpically driven, and entropically repulsive, okay? So the point of this is that all of these are favorable, but some of them are enthalpically driven, some of them are entropically driven, some of them are both. All right, and so what he's trying to get at here is that the different equilibria that you get.
Korea.
Yeah.
For the last equation, the beta-lactam globulin, how could a negative 234 minus negative 632 become a, I think it's a positive, right, of the delta G overall? I might be wrong.
No, this negative means it's a negative enthalpy.
Yeah.
But this negative contributes to the free energy. Negative is required to be the driving force. This a negative 632 opposes it. So to make that work, what you should do is you should write down this. Right? Plug these numbers into here and they should give you this. Okay.
So it's depend on the temperature too.
It depends on the temperature. That's exactly right. That's exactly right. And so I don't think this table tells you what the temperatures are, but if you just assume 25 degrees, I think you'll get these numbers. Okay?
Yeah, makes sense now. Thank you.
Okay. So what Van Holde is pointing out is these reactions can be various kinds of biochemical reactions involving proteins, monomer, dimer, monomer, hexamer, dimer, hexamer, stepwise, dimers, tetramers, hexamers, and they all have different combinations of enthalpy and entropy. And so the general question that he sort of is opposing is, without really presenting an answer, is where does this come from? How can a reaction be enthalpically driven or entropically driven or both? Okay, what causes these differences? All right, that's the point he makes. So what we want to stop for the moment.
Dr. Correa, could you go back to that formula again? The delta G? I feel like if we add 25 degrees Celsius is equivalent to 293 or 298 Kelvin. I think we got a positive value, not a negative value.
Notice this is kilojoules and this is joules.
Oh, okay.
Use kilojoules here. This is 234,000.
Okay.
And this is 298 times 632. So correct for kilojoules and joules, and you'll get the right answer.
Okay, thank you.
Okay. All right. So what we want to do, and now I have to go back again and open something, is go to this Ross and Subramania paper, which I put out there for you. Okay, and if we explode this a little bit, does this make this? Let's explode it a little bit more. Okay, so this is a paper published in Biochemistry in 1981. So it's 40 years old. It's more than 40 years old. And the title of the paper is Forces Contributing to Stability. And so what they're saying is that protein-protein interactions or macromolecule-macromolecule interactions have certain enthalpic or entropic driving forces. Where do they come from? Okay, and so you presumably have looked at this. Here's the table that I just had in the slide. Okay, And what I want to do is go through some of this with you so you see where this comes from. So what these guys did was they looked at small molecule interactions. So for example, they have these tables that involve ligand binding to lactate dehydrogenase. It's things like NAD, NADH, and ADP ribose binding. They're looking at the free energy of interaction. They're showing you what the enthalpies and the entropies are. And then they're showing you some binding of small molecules to alpha chymotrypsin, free energies, enthalpies, and entropies. Generally speaking, these all have negative enthalpies and negative free energies. There's one exception here that's positive. Okay, so these are small molecule interactions, and their binding to the binding sites are negative enthalpies and negative delta S's, negative entropies. All right. So what they're basically saying is that this type of small molecule interactions approximates what happens when protein-protein interactions occur. Read this highlighted section. The measured heat, which is the net sum of all thermal effects, will more readily lead to a direct determination of enthalpy change of association process than the analysis of equilibrium data by Van Hoff equilibrium. So they're beginning this paper by pointing out that all of these measurements are done calorimetrically. And what they're asserting is that the Van Hoff number gives you an answer, but it usually misses some of the details. It doesn't really do a good job for complicated equilibria or complicated processes. The calorimetric process will do a much better job. All of the data shown in this paper is calorimetric. So if there are multiple things going on, the calorimetric data is more believable. Notice here that the enthalpies are all negative for these small molecules. The entropies are mostly negative for this small molecule. And so does that inform us in terms of how protein-protein interactions occur? Down below, they show us another table. These involve self-associations between purines. Okay, so the rings in a purine derivative, you know what purines are from your understanding of DNA structure, base structure. These purines will stack very weakly. They have very weak free energies, favorable but small. They will tend to have negative enthalpies. They will tend to have negative entropies. Okay. And so a lot of the published data on small molecule interactions or on ligand protein interactions tend to show negative enthalpies and negative entropies. And so if you then imagine protein-protein interactions, this is the table in this paper, but it mimics the table in the book, show mixtures. Sometimes it's positive enthalpies, sometimes it's negative enthalpies. Sometimes it's positive entropies, sometimes it's negative entropies. Okay. Why is this different than small molecule interactions? The small molecule interactions suggest that the enthalpy should be negative and the entropy should be negative. It also shows heat capacity differences, which we'll talk about a little bit. The heat capacity differences tend to be negative. This is essentially the temperature dependence of the reactions, okay, and how these change with temperature. All right, and so what the paper then does is summarizes those data, and it goes through a long discussion. The method section is, the results section is sort of short. It ends with this table 4, and it summarizes what appears to be true for small molecule non-covalent interactions and then hypothesizes that it's sums of these that give rise to protein-protein interactions, okay? So notice, van der Waals contacts are negative-negative. Hydrogen bonding is negative-negative. Protonation is negative-negative. So those negative-negative interactions, negative enthalpies, negative entropies for small molecule interactions or ligand protein interactions apparently are determined by van der Waals contacts, hydrogen bonding, and protonation. When you have protein-protein interactions that are slightly positive, then those must be coming from the hydrophobic effect or maybe from charge neutralization ionic interactions. Okay, and so the idea is that when you have protein-protein interactions, let me go here. When you have protein-protein interactions, I'm looking for space. When you have protein-protein interactions and you have two surfaces that come together, the interactions that occur in here that stabilize that protein-protein interactions will be combinations of the hydrophobic effect, van der Waals contacts, ionic interactions, maybe protonation salt bridge interactions. Okay, to be combinations of all of these effects, sometimes giving rise to plus-plus interactions, that's approximately 0+, and sometimes giving rise to negative enthalpy entropy interactions. And I'm making the enthalpy entropy table here. It depends on how many of these interactions of various types that will determine the overall free energy for the reaction. Okay, and so what this table here is saying is the sum of the small molecule data reflects the fact that larger surfaces interact between proteins, and it's the sum of all of these interactions that contribute. And this is summarized in that table 4. Okay, so it's summarized here in this expression. Okay, sometimes it's hydrogen bonding or protonation or van der Waals, sometimes it's hydrophobic or ionic. So there's history to this. And they point this out in sort of the beginning of the discussion. The discussion begins here. And they point out that there have been a lot of papers published, primarily by this Clothia and Janin pair, who basically hypothesized that most protein-protein interactions are dominated by the hydrophobic effect. There was an earlier paper in the 50s that also proposed that the hydrophobic effect was the major driving force for protein-protein interactions. Okay, that 50s paper is this paper by Kausman. Okay, and so the data in table 1 and table 2 for protein association processes indicates that this hydrophobic interaction, okay, entropy favorable, enthalpy approximately 0 or unfavorable, because you're breaking the water-water interactions, generally are not satisfied. And in fact, the enthalpy entropy contributions are really going to be mostly negative from a lot of the criteria that we see in this discussion. Okay, and so it becomes a much more complicated question. They summarize this as a bigger hypothesis and they break it down into parts. Okay, and what they say is that sure, when a ligand or a protein interacts, there may be some hydrophobic interactions that are given by a positive enthalpy and a positive entropy, a negative heat capacity, but a favorable hydrophobic contribution to the free energy. That may partially be going on initially. Okay, so you initially make some kind of a close approach complex, but it's not the final answer. What happens is there's a rearrangement that happens at the interfaces, and it's not necessarily always clear that this happens in two easily delineated steps, okay? But there's electrostatic interactions and there's van der Waals interactions that can happen during rearrangement, and these will contribute different magnitudes of interactions that will give negative enthalpies, negative entropies, maybe some electrostatic interactions that are partially positive entropies, but it's this combination of all of these interactions that occur that give rise to the results in the table, okay? They also discuss partial immobilization, all right? And this is something that I don't think that I've mentioned to you yet, but the idea is that this small molecule is diffusing and tumbling around, and it has a certain amount of entropy. But when it binds to this molecule, this bigger protein, its mobility is diminished. And that partial immobilization means that its entropy is decreased. Its entropy, excuse me, is decreased. It's less mobile. That's unfavorable. Okay, it has a smaller entropy. It's actually unfavorable towards the overall reaction. So there's always a partial immobilization step that has to happen in addition to all of the other specific interactions that occur in the interface, okay? And so this partial immobilization is something that we always have to take into account because it's unfavorable, and all of the other interactions have to overcome that unfavorable immobilization, loss of mobility, okay, that give rise to the stable complex that is made. This immobilization or loss of entropy initially is often referred to as rigid body association, okay? And the idea is that none of this stuff occurs. The conformational changes, the rearrangements are not what we're talking about. Or imagine two rigid molecules simply bump up against one another. That's the term that you have to account for here. The literature, I think they say in the paper, this is approximately 20 to 30 joules, or maybe it's calories. I think they say calories. Other papers that we're going to talk about in a few weeks usually assume a value around 50, but it has some magnitude. These magnitudes refer to the initial immobilization that is overcome by all of these other conformational changes and establishment of specific kinds of van der Waals or electrostatic or hydrogen bonding interactions that end up stabilizing the complex. Okay, so you have to take all of that sort of into account. So there's a lot of discussion in this paper that I think is worth reading and thinking about. They go through each one of these interactions and try to make an argument for why the signs are what they are. Okay, they go through hydrogen bonding and van der Waals contacts, etc. They describe stacking interactions in some great detail. There's the hydrogen bonding. So the interactions that contribute to negatives, the interactions that contribute to positives, they go through all of this, okay? And the conclusion that they come to in the end is the observation that negative enthalpy, negative entropy requires primary driving forces from hydrogen bonding and van der Waals interactions, okay? And that hydrophobic effect is not absolutely the driving force for most protein-protein interactions. All right. There's some other discussion about other kinds of interactions that were discussed in this paper by Sturtevant that have to do with dynamic modes and sort of fluctuations in the protein. We don't have to get into all of those details. That entire paper is probably no longer trusted or believed. It was a great idea in 1977, but there's no evidence for it in most systems. There's probably some evidence in some of the enzymology that people do. Okay. So the data out of Van Holde shows an assortment of driving forces. And now you can look at this table and say, gee, where do these plus values come from? Where do these negative values come from? These favorable plus values for entropy suggest in those cases that there's a large contribution from the hydrophobic effect. These negative values suggest that there are van der Waals contacts and hydrogen bonding that is going on in those interactions, okay? And you can see that these zero values seem to correspond to consistent with small effects because the loss of hydrogen bonding, but then the gain of hydrogen bonding in the water contributes to nearly zero enthalpy change. But the negative values are consistent with an effect from other kinds of van der Waals contacts and hydrogen bonding, but they don't necessarily agree in both columns. So it suggests that it's sort of complicated, okay? And the same can be said for these tables, where when they're both positive, that's hydrophobic, but when they're negative, that must be from the negative contributions, van der Waals contacts and hydrogen bonding. It doesn't mean that there are no hydrophobic effects. It simply means they're small relative to these bigger phenomena that are going on. And one would need to look at more carefully, again, these are all calorimetric data to be trusted more, but one would need to look at the crystal structures to see what these interactions are and how they interact specifically, and make an attempt at summing up all of the contributions from the smaller interactions. Now, let me make one final comment here, and it has to do with this per monomer. The per monomer is supposedly giving you some sense of the magnitude of the favorable interaction and how that favorable interaction will vary on a per monomer basis. So if you have 8 monomers involved or 2 monomers involved, does the energy seem to make sense? And you can see that there's a lot of variation. You can have something that's as small as 2.7 favorable and something as large as 24 kilojoules per mole. Okay, so it tells you that the interfaces can be very different in size. The numbers of interactions can be very different. And so that makes a big difference in the overall magnitude per monomer. Now, I always comment at this point that I don't like the per monomer analysis. It should be per interface. There are 2 monomers here, but there's really only one interface. And so you really should put this on an interface basis, not monomer basis. And so this energy here is actually 31 because there's only one interface. This energy is really 42. There's only one interface. Only one interface. This energy is really minus 40, 41. Okay. Whereas here, it depends a lot on the structure. What's the structure of the tetramer? What's the structure of the octamer? And how many interfaces are there in that structure? Okay. And that changes what these numbers are. It's quite clear that the larger guys, this octamer obviously has far more interactions than this octamer. So even on an interface basis, that probably doesn't account for it. But I think it's a better way of thinking about it. It leads you in the right direction. Okay. So the take-home message is that it's a sum of forces in the protein-protein interaction phase, or protein whatever. If it was interacting with DNA or RNA, it would be the same thing, is a contribution of various interactions. Hydrophobic effect, van der Waals ionic, protein-protein interactions. Hydrogen bonding is the other thing that I don't put down here. That will contribute to the sign and the magnitude of the interactions, okay? This paper makes the additional point that I've already made to you. If the calorimetric and the Van Hoff enthalpies agree, that tells you something about two-state interactions. That figure in the paper showing you that there's multiple states going on, multiple phenomena, would demonstrate partially what's going on. What they're asserting basically is calorimetric data is just more accurate than Van Hoff analysis, which is generally accepted in the field. All right. There are two other points to be made here that I want to make with you. Papers today are becoming long again. A lot of papers that you read are long with huge supplements. But the reason for that is often because there's a huge amount of data. They're experiment after experiment after experiment, testing and evaluating all kinds of criteria that reviewers are demanding and that journals are demanding. Okay. It makes them difficult to read. You probably agree with that. The supplements can be hundreds of pages long these days. In the old days, okay, in the early 80s, in the 70s, in the 60s, in the 50s, often results were presented in a very compact manner. There was a short presentation of data, some detail about methods, but then there was a long discussion. How do we evaluate these data? And this paper is a really good example of that. Here's the results. Here's what we're sort of asking. And now let's see if we can understand and rationalize that table that has the signs of the enthalpic and entropic driving forces. So this is sort of a classic way of writing. The other thing that I want to say is that a lot of what you learn in graduate school comes from textbooks. Okay, we teach out of textbooks, generally speaking. John and I are not teaching out of textbooks, although John likes to use certain textbooks and he likes to teach out of them. But your cell and molecular biology courses tend to be out of textbooks. A lot of the teaching you get in the general courses are textbooks. But I'd like to point out to you that textbooks come from research papers. People summarize certain kinds of papers and tell a certain kind of story. The truth of the matter is that textbooks are often stolen from other textbooks. So this book by Van Holde, huge sections of it mimic other books. And he really stole sections from other textbooks, primarily a book by Tanford that I learned from in the early 70s when I was a graduate student. And in fact, is open on my desk right now because I'm rereading those sections. Okay. And so I want you to be aware of that, that what you get in a textbook is some author's or combination of authors' vision of how you put together a story in a textbook, how other people did it, how they choose to do it. But the raw data and the actual evidence really is a compilation of lots of really rigorous papers published by lots of authors. And that's where this stuff really comes from. Okay, and so Van Holde's section is really duplicating the Ross and Subramania type of analysis and the Tanford type of analysis. And Tanford's just one of the examples. I think in the the syllabus section on Canvas, I mention the books that I use as sort of the fundamental basis for a lot of what I teach. And many of us who went through the program that I went through still refer to those books. When I'm discussing stuff with one of my collaborators, we invariably open up Tanford and look for something. Okay, so this is a summary of what I just wrote on the as a summary on the slide, showing the contributions of different kinds of interactions. And what I'm pointing out to you is that interactions between macromolecules are sums. How many of these are there that gives rise to this? Okay, and then there's that figure from the paper that I went through describing multiple interactions, okay, that contribute to the stability of the complex. Okay, so Van Holde then begins to get into the weeds a little bit. Okay, the pathways. So I took the time to go through in more detail where the signs come from that contribute to the stability of those complexes. But now what Van Holde is trying to do and what we want to do is begin to ask questions about equilibrium constants and where do these equilibrium constants come from? And how do you analyze them? How do you analyze data? And how do you think about these kinds of interactions? So I think this section is labeled simple case or something like that, where, no, maybe it's just a continuation, where there's a monomer dimer and you can write down the classic equilibrium constant concentration of dimer divided by monomer squared. If you write down a term that involves the total concentration of monomer, there's the concentration of monomer twice the concentration of dimer. So this gives the total concentration of monomer in the reaction mixture. And then if you solve for dimer in this way, plug it in to the equation up above, you'll have a monomer term, another monomer term squared. This will generate a quadratic. And then you can rearrange that quadratic to give you the amount of monomer divided by the total concentration of monomer in terms of a quadratic solution. And then in the book, there's a plot, basically, which is the concentration of monomer. This is written in moles per liter, I guess. Yes, this is written in moles per liter. And what it's showing is that as you vary the total protein concentration for a monomer dimer equilibrium, the concentration of monomer decreases relative to the total concentration. You start out near 100% or 90%, and it diminishes down to 0%, or this looks like 20%. The shape of this curve is essentially the same, but it's shifted by the midpoint of the equilibrium. So this equilibrium constant is big, 10 to the 8th. So the midpoint at 50-50 gives you the equilibrium, the dissociation constant, or it gives you the concentration, total concentration at the midpoint of the reaction. Okay, so on a mg per mil basis, this is 0.0002 mg per mil. Or for a weak equilibria, it begins to dissociate at 2 mg per mil. And the shape of the curve, when it's the affinity constant of 10 to the 4th, you have dramatically different progression curves. The point that's being made here is that if I want to measure this equilibrium constant out here at 10 to the 4th, to see a change in the monomer dimer distribution, I basically have to do experiments at 2 mg per mil. If I have something that has an affinity of 10 nanomolar, 1 times 10 to the 8th liter per mole, then I have to do experiments in the sub mg per mil. Okay, I have to be working in the microgram per mil region. This is 2 micrograms, okay? And so you can do experiments to measure the amount of monomer dimer, but you have to be working in very different concentration regimes. Okay, so this requires high concentration. This requires low concentration to be able to make the measurement. This is really an introduction to methods. He then gets into another way of talking about this, and he expresses it as an average molecular weight, fraction monomer, fraction dimer, times the molecular weight of the monomer and dimer. He goes through a derivation that I won't go in detail, but expressing the equilibrium constant in terms of fraction monomer and fraction dimer. And then expresses this in terms of the average molecular weight. Notice this is a weight average molecular weight versus the monomer molecular weight. And if this is a monomer dimer equilibrium, then you're watching this ratio go from 100% monomer, to 2, 100% dimer, over again some concentration regime in terms of mg per mil, okay? So if the experiment that you're doing is measuring the apparent molecular weight, the weight average molecular weight, to make the measurement with the low affinity case, you can make experimental measurements in the mg per mil range. And notice from 1 all the way out here to 10, there are big changes in molecular weight that you will see. But to make measurements of the change in molecular weight for the high affinity, you have to do all of your experiments in the sub mg per mil micromolar region, because it's all happening down here. Okay, often when we do these plots, we put them on a log scale to spread these out. But again, it's an attempt to give you an understanding what concentrations you need to make measurements at to see the change, and it depends on the equilibrium constant. Okay, and so that's the point that's being made here. All right. So that's point number 1 that the book is making, that depending on the affinity is determined by those enthalpic and tropic contributions that I mentioned. But depending on the affinity, the measurement ends up having to be made in different concentration regimes. I skipped it. There's a figure in the book that's basically binding to DNA sort of experiment, and at really high affinities, it's pointing out that you need to be working in the sub-nanomolar for some of these experiments, and you have to be really creative in how you make the experiments. All right. So the next point that he makes is he summarizes what I will tell you are Scatcherd rules. This is something that was proposed in 1949 by a guy by the name of Scatcherd. And when he proposed it this way: how many, how tight, where, and why. Okay, so how many binding sites are there? So what Ken did is he turned that into a sentence: maximum number of moles of ligand that can be bound per mole of macromolecule. What are the numbers of sites for a ligand designated A? How many ligand binding sites are there? How many? How tightly do they bind? What are the equilibrium constants and other thermodynamic parameters that we'll want to get at for binding of this ligand to each site? Okay, so how many N, how tight K? Is the equilibrium constant for the binding of ligand A to each of the sites independent, or is it cooperative? Okay, does it depend upon how many other sites are occupied? It's related to the second equation or the second question, because how tight will vary with the number of sites bound. So if there's cooperativity, the first site binding will be different than the last site binding. So the where is sort of a reflection of where are the binding sites and do they communicate with one another? Okay. And then the final question, why, has to do something with regulation, has to do something with potentially cofactors are the equilibrium constant for the binding of ligand A modified by the binding of ligand B. Okay, so the example that we have already talked about in Med Biochem, the example that we will be talking before we're done next week, oxygen binding. Oxygen binding to hemoglobin depends on proton binding. So oxygen binding to hemoglobin is pH dependent. It depends on the binding or the Bohr effect, proton binding, that affects the stability of a salt bridge that influences the conformational changes in the hemoglobin tetramer. So how many N, how tight K, is it cooperative? Is there allosterism, positive or negative allosterism due to other ligands? Okay, and so Ken has a kind of a big discussion of this in the chapter. Now, at that point, he then begins to describe, and he goes into, I think that section is called definition of binding. And he begins to describe this in a slightly different way. And this is the classic way that this was introduced. I've written this as a V sort of Tyndall. Don't confuse this with V bar, the partial specific volume. This in the literature, the symbol is often a symbol that I would call nu. Not sure if the right way of spelling it. It's sort of a U-ish symbol. It almost looks like a mu. I'm sorry for the confusion about this. Every book sort of does a different way of doing this. Ken tends to do it this way, and it really looks like a V bar. And what he's doing is defining what this is. And so up above, we already did this. The total concentration of ligand is the free concentration of ligand plus the bound concentration of ligand. This accounts for everything. Either you're free or you're bound. And so nu is defined as, that should be a sub B, how much is bound divided by the total. Okay, and notice it's the total protein concentration here. Okay, and so how much is bound per total concentration of protein? This essentially is a way of getting at the number of binding sites. Initially, you have nothing bound, and then there's some progression as you raise the protein, raise the free concentration. All right, and we normally want to plot this as free concentrations for reasons we'll be talking about. And then,
yeah.
Yes.
When you say free, is it unbound?
Unbound.
Okay.
Yes,
Okay.
because the driving force in the chemical potential expressions is free concentration. When you write down an equilibrium constant, for example, ATP divided by ADP and PI, these are all free concentrations.
Yeah, yeah.
Okay.
Okay.
If ATP is bound to something, it doesn't contribute. If ADP is bound to something, it's not contributing to the overall free energy for this reaction. Okay.
Yeah, yeah.
Okay. When you have a monomer dimer, 2A going to A2, and you write the equilibrium constant down as A2 over A squared, how much is dimer? How much is monomer? Unreacted, reacted. Okay. We will use the term later, ligated. How much bound is the ligation fraction? How much ligand is bound to the protein? All right. So this is a general expression just to show that it might have, for example, this tends to suggest that there are multiple equilibria in here, and you get changes across this with multiple equilibrium constants. Okay. So nu concentration bound divided by total protein concentration. The other expression that he derives is what he calls a delta X, or a fractional saturation, So a change in some kind of a measurable parameter. So a change in X plotted versus total ligand concentration. Okay, and so this, for example, could be a change in absorbance or a change in fluorescence or a change in some kind of a sedimentation coefficient that refers to a complex. So you're measuring something and you're summarizing it as a delta X, and you're using that as some way of knowing how much is bound. In the example that we're going to be coming to, we can use absorbance, for example, in oxygen binding to hemoglobin. And the change is reflected in the color. When oxygen is bound, the hemoglobin is red. When oxygen is not bound, the hemoglobin is blue. Okay? And so there's a color change having to do with electronic change in the state of the oxygen. All right? We won't talk about it a lot, but we'll get into it with some papers that we talk to. And so that's the delta X. How much is red? How much is blue? When you put that thing on your finger in the hospital to measure your pulse and to measure your oxygen saturation, that's what it's doing. It's looking at the spectra and calculating the fraction red and the fraction blue. The delta XT is what the maximum change would be if it was saturated. And so the delta X over the delta XT is essentially the fractional saturation. Delta nu gives you the sign of the magnitude of how much is bound per protein. That's this expression. And then N is the total number of sites, how much the maximum number is. And so that ends up being a theta term that we can express as a fractional saturation. So this goes up to the delta X total, but we could rescale this so it goes from 0 to N, or it can go from 0 to theta. It just depends upon what way you want to express it. So fractional saturation is one way of doing it. The advantage is you go from 0 to 4, or you go from 0 to 1, meaning 100%. Okay. And when you do this in a theta, then you can superimpose things like myoglobin and hemoglobin on the same curve. Okay. And so the myoglobin might look like this, and the hemoglobin might look like this, but they go from 0 to 100, even though this one is going to 1 and this one is going to 4. Okay, so that's one of the advantages of doing fractional saturation. All right. So this is a typical binding curve, the dotted lines. He mentions the solid lines as a strong binding case. And this is a binding example where everything you add binds. So this is tighter than 10 to the 8th. And every little bit that binds gives you a change, but it never gives you a partial change. In other words, there's no free, there's only bound. And it goes and goes and goes until it's saturated, and then it doesn't change. And that gives you an indication of the number of sites. A total divided by P total. This becomes very difficult to analyze. We talked about this data in the calorimetry data. There were examples in the titration calorimetry where everything gave the same signal and then it went to 0. And that was a tight binding experiment, as opposed to a titration where you could actually see a gradual change. So if you go back and you look at the titration calorimetry data, it mimics this type of a figure. Okay. All right. So in the book, it goes to what is called simplest case and multiple equilibria, and that's where we're going to pick up next time. Okay, I almost timed that perfectly. Okay, So this is where we are. Let me save this. All right. And then let me stop recording. To stop recording, I have to stop sharing. And then down here, it's over here. Pause, stop recording.